Chapter 25, part 2, energy and momentum in electromagnetic waves. So the energy density in the electric field is half epsilon 0 E squared. This is the permittivity of the free space. So you are looking at the half the value of that times E, which is the value for the electric field, times to the power of 2. And in the magnetic field, we had the same thing, but we were dealing with permeability of free space, or mu 0, 1 over 2, 1 over mu 0, or 1 over 2 times mu 0 b squared. But we know that the electromagnetic wave is the combination of both the electric field and magnetic field. So therefore, the total energy density is when you add them up. So you add the U of E and U of B, so you're dealing with half of epsilon 0 E squared plus 1 over 2 mu 0 B squared to have the energy density of electromagnetic wave. So which we have it right here. Okay. It can be shown that the energy densities, or U, in the electric and magnetic fields are equal. Okay. So if we have U of average of half of epsilon 0 E RMS, or root mean squared to the power of 2, plus half of mu 0 B RMS, or root mean squared to the power of 2, then we'll have an average of U, which then this could be shown to be of epsilon 0 E RMS to the power of 2, or 1 over mu 0 B RMS to the power of 2. Okay, so in other words, this would be the average value for electromagnetic wave, and this would be the average value for the electromagnetic wave, and they are equal. In other words, if I have epsilon 0 E RMS to the power of 2 being equal 1 over mu 0 B RMS to the power of 2, which is the U average, then if I just multiply everything by half, so 1 over 2 here and 1 over 2 here, then we have this relationship, meaning that the energy densities both for the electric and magnetic field are equal. And then so what we can write is this. We can write one over 2 epsilon 0 ERMS to the power of 2 being equal to 1 over 2 mu 0 BRMS to the power of 2. And then I can put everything under the square root, right? I can put whatever we have on the right-hand side under the square root, and then whatever we have on the left-hand side under the square root, and this equal sign will still be valid, because whatever that happens in right-hand side, the same thing happens on the left-hand side. So if you put the right-hand side under the square root, and if you put the left-hand side under the square root, then this equality is still valid. So this can be transformed, okay, in this way, because e to the power of 2 is just e, and then 1/2 and 1/2 will cancel out. So you're dealing with the square root of epsilon 0 here and the square root of mu 0 here on, in the denominator. So e is 1 over square root of epsilon 0 mu 0 b, but we already know that this guy is c. This guy is the speed of light. So E is C times B. Okay? So intensity of electromagnetic radiation. So we know that these radiations are because of the oscillations of charges or atoms and molecules. The energy a wave delivers to a unit area in a unit time. The unit area means in 1 second. In a unit time, the unit time means in 1 second. The unit area means 1 meters squared, okay? 1 meters squared. It's called intensity, or intensity of light, which is the delta U over A times delta T. This is the unit area times unit time, okay? I can write this delta U, which is the energy density, okay, the amount of energy inside the volume, as if I have a cylinder here, and the cylinder, the volume inside the cylinder, okay, you have one side, this is A, and this is C delta T. Remember, X was VT, okay? So X, which is this length, is V is the velocity, which is the speed of light, and T is the time it passed, which is delta T in our case. So X times A will give us the volume for this. So that's why I have A times V or C delta T. A times C delta T here. So I can multiply the energy, okay, times this value, which is the volume here, and get the delta U, or the change in the energy, okay? And then what's happening is that this delta T and this delta T will cancel out. This A and this A will cancel out, okay? And then you are left with U times C, which we can see here. So I is the energy density times the speed of light, which is the intensity. So this is the formula for intensity. Okay. Momentum in an electromagnetic wave. So if I substitute the energy density here, which is U, okay, so whatever the formula you had for U, remember what U was? Half epsilon 0 E squared plus 1 over 2 mu 0 on the denominator B squared. So if you multiply this by C, you will get I. And this is exactly what's happening here. So also this is a very, very, very important formula in this case, and in this chapter. So I'm going to highlight it. And an electromagnetic wave also carries a momentum, and the momentum was a very simple definition of momentum was mass times velocity will give you momentum. Momentum has other definitions, but this is the very basic momentum definition that we did in Physics 1. But in order to find the momentum of the electromagnetic wave, you have to divide the energy density of these electromagnetic waves by the c, which is the speed of light, to get p, or the momentum. We also have something called radiation pressure. The radiation pressure, because of these momentums of particles. So the momentum, remember, light, okay, has two different definitions. It could carry a mass, so it could be particles, and it could be a wave, okay? We believe that it can be both at the same time, depending on the measurements that we do. So therefore, it can exert a pressure, which is called radiation pressure, on objects, okay? For example, what you can see is a comet, and the dust tail, this is the dust tail, change the color, okay? This is the dust tail, and this is the ion tail. The dust tail and the ion tail are there in the comet, but the radiation pressure is responsible for the curvature. So there's a curvature here in the dust tail of the comets. So this is called radiation pressure, and that pressure is I over C, or in other words, the intensity and the average intensity over the speed of light. So this is also very important. I'll go repeat these one more time when we get to the summary of this chapter. So, polarized fields. The polarization of the electromagnetic field refers to the direction of the electric field. So whichever direction that the electric field is located at, that's the polarization of that electromagnetic field. So here I have an electric field that is along the z direction, and a magnetic field along the y direction, okay? So the electric field is along the z direction, and that is the polarization direction. Remember, the polarization of an electromagnetic wave refers to the direction of its electric field, okay? Whatever the direction of the electric field is, that's the direction of the polarization. So here it is along the z direction, so that's why my polarization is along the z direction. Here it is with respect to 60 degrees with respect to y, so it is 60 degrees above y direction. So that's why if I ask you what the polarization direction is, you can say that it's 60 degrees with respect to y direction. So whichever direction that the electric field has, that's the direction of the polarization. Polarized versus unpolarized light. So polarized light has its electric field all in the same direction. So all the lights that are going in through will have the same electric field in one direction. Okay, so polarized light has its electric field all in the same direction. Unpolarized light has its electric field in random directions. So that's what you can see here. So I have a propagation direction, or the direction of the velocity of the light, but then I have what I have here is a kind of a filter, okay, which can polarize these incoming light. So we have a polarized beam going through, okay? So in other words, I have this beam coming in, but all the E, or all the electric field, are in this direction, okay? Let's say around, let me actually try to give you a very good idea of what I'm talking about by giving you a reference point. So let's say that this is X, this is Y, and this is Z. So all of the E in this case are along the Z direction. So my polarization is along the Z direction. And this filter is filtering. In other words, it is polarizing my beam of light along the Z. It does not let anything to go through other than the ones that are along the Z direction, okay? Other than the beam of electromagnetic waves that has its electric field components along the Z direction, okay? Now, compared to something unpolarized, okay? Compared to something unpolarized, this E could be in a random directions, does not matter. But a polarized field, in a polarized electromagnetic field or line, it will be always along one direction. So that's the filter that I was just talking about. A beam of unpolarized light can be polarized by passing it through a polarizer, okay, which is like a filter, which allows only particular component of the electric field to pass through. So here, if I have this filter and pointing in this direction, let's say that this is Z direction, again, this is Z direction, this is X direction, and this is Y direction. Okay, so let's say that I have put my polarizer along the Z direction. So the incoming wave will be polarized along the Z direction. But if I had this filter or this polarizer along the X direction, for example, then this incoming light, or this incoming electromagnetic wave, will not pass. So this is acting some sort of like a filter for me. Okay, so it doesn't let anything to go through if it's pointing in this direction. Now, we have something called analyzer, and the analyzer is basically letting the polarized light to go through, but it will rotate the direction of the direction of the oscillations of the electric field. Let's take a look. We have a polarizer that transmit the component of light in the polarization direction. Okay, so I have a incoming light which is polarized, vertically polarized light, okay, and this is the direction of the E field, by the way, okay, with initial intensity of I0. All right, this is a wave coming in, and this is the direction of the oscillations for the E field, or the electric field. It will hit my polarizer, and then this polarizer or analyzer in some sort has a an angle associated with it. In other words, when this hit this polarizer or analyzer, this will be bent towards this angle. This will be bended with an angle of theta. Okay, this will be rotated with an angle of theta. So at the end, I have a E field that is bended, okay, theta degrees, 60 degrees, 30 degrees, 10 degrees with respect to the direction of the polarization. This would be the exact same value that I set my analyzer to do, okay? So then the outcome, the out, will have a value of intensity as I0, which was initial, times the cosine squared of theta, okay? Times the cosine squared of theta. And the reason for that is pretty obvious. The reason for that is because this E has a component along this direction, okay, which is E cosine. And thus, if you want to find the intensity, you have to square it. So I have I being I initial times the cosine squared of theta, okay? This is exactly what it's talking about. Since the intensity of light is proportional to the square of the field, okay? Square of the field, the intensity is proportional to the square of the field. Remember this? Let me go a couple of slides back. Here we go. I, which is the intensity, okay, is proportional to E squared and B squared. So it is proportional to the field to the power of 2. So since that's happening, the intensity of the transmitted beam is given by the law of Mullis. So that's why I is I0, which is the initial intensity times the cosine squared of theta. The light exciting from a polarizer is polarized in the direction of the polarizer. Okay. In other words, as I said, this polarizer is acting for me like a filter. Okay. So it will polarize my light in the direction that I want and the direction that I'm setting my polarizer to. Okay. Okay. Now, if an unpolarized beam, so previously we were dealing with a polarized light going through an analyzer, okay? So we were getting I0 cosine squared theta as my final intensity. But if I had an unpolarized incident beam, so initially, if I had an unpolarized incident beam coming through, if an unpolarized beam is passed through a polarizer, the transmitted intensity is half of its initial intensity. So I have an unpolarized beam. It means that this is the E field for one of them, and this is the E field for the other one. This is unpolarized. And I let it to go through my polarizer with an angle of theta, or my analyzer with an angle of theta. Then it will be bended, or it will be polarized with this angle. Okay, so it will only let the lights with this angle to go through, but then the intensity of outcome, the outcome intensity will be I0 over 2. It will be half of its initial value. Now let's set everything together. So I have a unpolarized incident beam going and coming to hit my polarizer. Okay, so what we know is that this polarizer will, reduce the intensity to half. This is exactly what we have here. Okay, so I have an unpolarized beam going through my polarizer, and then it gets half of its intensity out. Okay, now this wave is polarized because I set my polarizer in this direction. So this beam is polarized. Okay, this polarizer does not let anything go through unless it is along this direction. Okay, and then I will let this to go through something else. I will let this to go through an analyzer, meaning that this is now polarized. Okay, this is now polarized, and it will go through the analyzer. The analyzer will get the polarized field and rotate it towards the direction that I want. so rotate it to the angle of theta. Okay, so this is now rotated with an angle of theta, right? And now I have initial value, which is I over 2, right here, initial value, which is I over 2 times cosine squared of theta. So this way, I get an unpolarized incident beam. I let it go through my polarizer, getting half of its value out, and then I will let it go through my analyzer. So the analyzer is rotating the polarized beam to the direction that I want, and I'll get the intensity of half I0 cosine squared omega t. And we know that cosine squared theta, or cosine squared, is something is equal to always positive. Okay, and this is always between 0 and 1, and it's always positive. So let's take a look at a summary of this chapter. Electromagnetic waves are traveling waves of oscillating electric and magnetic fields. Electric and magnetic field in an electromagnetic wave are perpendicular to each other. And the direction of the propagation are also perpendicular to that. So you have the electric field in this direction, you have magnetic field in this direction, and then you have the direction of propagation or the direction of the velocity. In order to find it, we use the right-hand rule. Right-hand rule will give us the direction of the field. Put your forefingers along the direction of the E field, bend them or curl them towards the B, and then your thumb should show you the direction of your propagation or your velocity. So you have this, and then you bend them, so you kind of get something like that. And then your thumb should show you the direction of propagation. Any accelerated charge will emit an electromagnetic wave. Electromagnetic wave can also travel in vacuum. It's not like a sound wave. It needs a material. It can go through the vacuum. The speed in a vacuum is always the same, 3 times 10 to the 8 meters per second. If the observer or the source of the electromagnetic waves travels in time, travels with some speed, with a speed of u, for example, then we have something called Doppler effect. The Doppler effect does not affect the speed, but it affects the frequency. The Doppler affected frequency is the rest frequency times a value, and that value is 1 plus and minus u over c, okay? U is the speed of the observer, or the source. C is the speed of light. Electromagnetic wave can have any frequencies, okay? And we know that how they are related. The entire range of frequency is called the electromagnetic spectrum. Sometimes it's called electromagnetic spectrum of light. Name portion of the spectrum from the lowest frequencies to the highest frequency are the radio, microwaves, infrared, visible light, ultraviolet, X-ray, and gamma rays. So here is a relationship for the frequency and wavelength. If you multiply frequency and wavelength, you'll get a constant value, which is the speed of light, which is 3 times 10 to the power of 8 meters per second. And in order to find the energy, all you need to do is to multiply the Planck constant, which is a constant value usually be given to you in problem or exercise or whatever that you're dealing with, and then times the frequency. So if something has a high frequency, then it means that it has a high energy, okay? The energy density of the electromagnetic wave is given with this relationship, 1 over 2 epsilon 0 E squared plus 1 over 2 mu 0 B squared. Or I can write it down as epsilon 0 E squared of RMS or 1 over mu 0 B squared RMS, okay? And then using this relation, we kind of define that they are all equal. In other words, half epsilon 0 E squared is 1 over 2 mu 0 B squared, and then using that we derive E is C times B. C is the speed of light, And then the intensity of the electromagnetic wave was U times C. So whatever that I have here on top, I have to multiply that by C to get the intensity. So that's why you have an extra term here, or an extra value here as C, or the speed of light. And the momentum of the electromagnetic wave is P, U over C. This U is energy, okay? So P is energy over speed of light, okay? And the radiation pressure, the pressure that is due to these materials, the light, is I of average over C, or the intensity of average over the speed of light. The polarization of the beam of light is happening in the direction of the electric field. So whatever the direction of the electric field is, we can say that that's the direction of the polarization. So that's the direction of the polarization, for example, here. And a polarizer transmits only light whose electric field has a component along the polarizal axis. So if you have a polarizer that it's being directed, or it's being placed in this direction, and then you have a beam of light going through, okay, this polarizer will only let the light going through if they have the E field along this direction, okay, along the polarizer axis. And then an initially polarized beam of light encountering a polarizer at an angle of theta has transmitted intensity of I0 cosine squared of theta. This is called analyzer as well. The transmitted intensity of initially unpolarized beam of light. So if it was unpolarized initially, unpolarized beam of light will be half of its original value. Light scattered from the atmosphere is polarized when viewed at a right angle to the sun. And then when light reflects from the horizontal surface, it is polarized, it is partially polarized in the horizontal direction. This is partially polarized. Okay, this is the end of a very small chapter, chapter 25. So let me know if you have any questions.